All right, in today's lesson, we're going to take a look at how the human brain, that 3-pound hunk of flesh in our head, speaks and communicates. Now, in order to understand how this works, there's two structures we need to know. The first is the neuron, and the second is the synapse. So let's just start with the neuron. Just like every other organ in our body, the brain is made up of a number of cells. And a neuron is the particular name given to the special type of cell that makes up the brain. In fact, your brain is made up of about 100 billion neurons.
Wow. But it's just like every other cell in the body, right? Like an ordinary blood cell?
In a way, yes. So just like every other cell, a neuron has a cell body. And inside of that cell body, it has the nucleus, the mitochondria, all the things that make all cells work. But what makes it unique is its structure. Beyond that cell body, it's got a bunch of additional stuff. So just taking a look at this neuron now, what's one of the first things you notice that's unique about it?
It's got these branches coming off it, the dendrites.
Bingo. So those dendrites are made of the same material as the cell body. So in a really real way, you can think of it like branches kind of coming out of a tree. Now, in terms of communication, information comes into a neuron through those dendrites. So there's your input point. Now, what's the next thing you notice?
There's this long thing that's coming off it, the axon.
Yep, so the axon is made of different material than the cell body. So it's technically considered a totally different structure. So one of the first things we have is called the axon hillock. That's the area where the cell body and the axon meet. Now the axon is this long tube, and in terms of communication, the communication signal must pass down that tube and through it in order to get to the end of the neuron. Now, do you notice the kind of myelin sheath, the yellow wrapping around that axon? So that's done for insulation. The myelin sheath protects that axon, protecting it from the external environment, essentially blocking it off. Now, in between, you have what's called the nodes of Ranvier. These are areas where the axon is exposed to the external environment. And we're going to see in terms of communication what that means shortly. Now, notice that the axon ends in a bunch of, it kind of splits off and ends in a bunch of terminal buttons. So what do you think those are for?
Well, if the information comes in through the dendrites and then flows down the axon, does it leave the neuron via the terminal buttons?
Absolutely, too easy. So there's your output point. Information leaves the neuron through those terminal buttons. Now, that's one neuron, that's cool, but what we want to know is how different neurons, two neurons, talk. So in order to understand how communication happens, there's one more structure we need to know, and that's called the synapse. So we have 100 billion neurons in our head. We have 100 trillion synapses. And the synapse is an area of communication, the point where two neurons speak. And what's interesting is if we zoom in real close, you'll see that the two neurons don't actually touch. There's a small gap right between them. So let's zoom in and see what the parts of a synapse are. So we've got three major structures, and we start with the presynaptic terminal. Now, thinking back to a neuron and how information comes in through the dendrites, out through the terminal buttons, what do you think the presynaptic terminal actually is?
Is it one of those terminal buttons?
Exactly. So this is the terminal button of neuron number one. This is where the information comes out of the first neuron. Now, do you notice inside that we have a bunch of vesicles and neurotransmitters? Mm-hmm. So this is how we communicate across that synaptic cleft, that gap we were talking about earlier. It's called the synaptic cleft, and these neurotransmitters are how we get our messages across that into the postsynaptic terminal. So if we got the terminal button is a presynaptic terminal, what do you think this postsynaptic terminal is?
Would that be one of the dendrites from neuron number 2?
Exactly. This is the input point for the next neuron. So this is your dendrite. So you have terminal button, synaptic cleft, dendrite, postsynaptic terminal for the next neuron. And the last thing I want to point out are the receptors. So the postsynaptic terminal is lined with a bunch of receptors. And this is going to become important once we see how this all works. In fact, are you ready? You want to just see how this works?
Yeah.
All right, so we've got our parts down. Let's see how communication works. Let's start by just zooming in on one neuron. Now, inside of a neuron, you've got a bunch of ions. Ions are just charged molecules. It's kind of like a magnet. So in this case, we have chloride, which is Cl negative. That's how you know it's negative. So we tend to have a lot of negative ions inside of a neuron.
Okay. So you said it's like a magnet. Magnets have positive and negative sides.
Yep.
So there are positive ions as well?
Absolutely. There's tons of positive ions. Probably the most prominent is sodium, which is Na+. That's how you know it's positive.
And these are inside the neuron, same as what?
There are some in there, but for the most part, the positive ions are outside of the neurons. So what we have is we call this polarization. The idea is that inside of the neuron is far more negative than outside of the neuron. It's polarized. And when a neuron is just sitting there, not doing anything, not firing, that polarization usually sits around negative 70 millivolts. This means there's 70 millivolts more negativity inside of the neuron than there is outside. And because this is what it just typically is when it's just sitting there not doing anything, we call this the resting potential.
And what happens if that changes, like if it becomes more negative or positive?
This is where communication starts to happen. So that's an awesome question. So let's shift now real quick over back to the axon hillock and see how this all works. So at the axon hillock, where the cell body and axon meet, a lot of ions are always coming and going and fluctuating and moving. And you've always got some positive there and negative. Now, sometimes at the axon hillock, you're going to get a bunch of negative ions. When this happens, the inside becomes even more negative, and we call that hyperpolarization. So if the resting potential is negative 70 and you're hyperpolarized, what do you think you might be at?
Like negative 80 or 90 or 100?
Bingo. Yep, you just keep getting more negative. Now, occasionally, and here's where the fun starts, you're going to get a lot of positive ions at the axon hillock. So here's where you start moving from hyperpolarization into depolarization. So let's say this is going on. So we're negative 70, we're just sitting here, and we'll pretend a bunch of positive ions just start to flood in. So we go from negative 70 up to negative 65, up to negative 60. Eventually, we're going to hit the break point, negative 55 millivolts. When this happens, you get what's called an action potential. And this is essentially the neuron firing. This is the signal. When you hit negative 55 millivolts and an action potential starts, that's the sign that it's time to start communicating. I'm going to start a signal.
And that's only when it hits negative 55. If it's anything less than that, so negative 56 or 57, does anything happen?
Nothing at all. So we call this an all or nothing action potential. And the idea is simple. Once you hit this level, you get the same action potential every time. It doesn't matter if you go to negative 50, negative 30, or if you're before it. If you're before it, it's never going to happen. After it's never going to be any stronger or weaker or faster or slower. You're just going to have an all or nothing action potential. Now, this action potential is essentially that polarization, that negative 55, simply moving down the axon. So it starts at the axon hillock, and just like an electrical signal, we have to take that and just pull it all the way down the axon, and that's the communication.
Okay, and how does the myelin sheath affect this?
Good question. So remember we said the myelin sheath is for insulation, right?
Yeah, as in like it warms it up?
That's what, no, most people think insulation like home insulation, like it kind of protects it, right?
Yeah.
In this case, we want to think of it like electrical insulation, in that what it's doing is it's blocking off that polarization between the axon and the outside environment. So essentially the axon, wherever there's a myelin sheath, isn't touching outside, so it's not more negative or positive, it's essentially isolated. So in terms of an action potential, whenever you see a myelin sheath, that negative 55 polarization doesn't have to pass there. It can just skip right past it. And here's your nodes of RANVA. The action potential actually jumps between each of the nodes of RANVA, skipping those myelin sheaths. And we call this saltatory conduction. Rather than one signal, it jumps really quickly between those nodes.
Yeah. And why is that important? Why is it important that it jumps quickly between nodes?
It's important because of speed. So imagine if that signal had to go all the way. It has a lot of ground to cover, but in this way, it can just keep jumping really quickly and skipping. So it's got a lot less ground to cover. So the brain speaks so quickly because of this myelin sheath and nodes of RANVA. That's how it just moves so dang fast. So now eventually that signal is going to get to the end of the neuron. You're going to have your action potential, it's going to hit your terminal button, and now it's time to jump to the synapse.
Okay, so like an electrical signal, does it hit the terminal button and then kind of flip a switch and turn it on?
Close. It does flip a switch in a way. That electrical signal gets to the terminal button, and what it does is it opens up a receptor. And when that receptor is open, calcium floods in. When calcium comes in, that pushes the vesicles to the edge of the terminal button, and those vesicles then release their neurotransmitters into the synaptic cleft. And here's how we have communication between neurons. So have you ever heard that the brain is an electrical chemical system? Here we go. On the inside of the axon, we had that electrical signal. But here at the synapse, that electrical signal becomes chemical in the form of these neurotransmitters. So we have an electrical chemical communication system.
Okay, so these chemicals, the neurotransmitters, get released in the synaptic cleft, and then do they kind of swim across to the receptors on the other side?
That's what we thought for a while, that they kind of propelled themselves over to the receptors. Turns out they don't at all. Neurotransmitters don't do much of anything. They do what's called passive diffusion. They just kind of sit there and float around. And every once in a while, when you're lucky enough, one of those neurotransmitters will hit one of the receptors on the other side. Now, 9 times out of 10, they're not going to fit. A neurotransmitter is going to hit a receptor and nothing's going to happen because they have to fit like a lock and a key. But every once in a while, you'll get the right neurotransmitter and the right receptor. They'll passively diffuse, they'll hit each other, and when that happens, a gate is open and new ions then flood into the postsynaptic terminal, that kind of dendrite of the next neuron.
Okay, and are these the positive ions or the negative ions?
Both. That's a great question. So both positive and negative come flooding into that new neuron. And so because we've now gone from neurotransmitters, chemical, back into ions, which is electrical, we now go back to that idea of a potential. So we call this the synaptic potential. Here's where we start to get a new electrical signal flooding into the new neuron. And remember before, when we were looking at neuron 1, we said this whole thing started with ions kind of fluctuating at the axon hillock. Sometimes you get positive and negative, and kind of their distribution is what determined whether or not a neuron fires. Guess where those ions are coming from?
They're coming from the synapse.
Bingo, the synaptic potential. These ions flooding in are the same ones that flood into the axon hillock and determine whether or not this next neuron is going to send a signal of its own and fire.
Yeah. Okay, so synaptic potential sounds similar to an action potential. Do they work in the same way?
No. So an action potential, remember we saw, was all or nothing. It's just going to do its thing.
Yeah.
Synaptic potentials aren't all or nothing. They're actually graded and decremental. So here's what I mean. By graded, I mean that not every neurotransmitter and every receptor are going to click. So at every synapse, you get different amounts of ions coming in. Sometimes you're going to get a perfect match and all these ions are going to come flooding in. Sometimes, not a great match, and just you'll get a little trickle of ions. So this is graded. Sometimes it's big, sometimes it's small. What I mean by decremental is this, is the further away a synapse is from the axon hillock, the longer those ions have to travel. And as they're traveling, they're starting to lose their signal. So when you have a synapse that's really far away from the axon hillock, by the time the signal gets there, it's very weak. But if you have a synapse that's right next to the axon hillock, that signal gets right in there. It's a really strong signal, and it'll play a bigger role in whether or not that next neuron says, yep, we're going to depolarize and we're going to fire.
Yeah, okay, so these ions come from all these different synaptic potentials, from close and far away, and then they gather at the axon hillock, and if there's enough positive ions, then it generates an action potential and the whole thing starts all over again.
Bingo. And that's communication in the brain. Just this cycle. Action potential into synapse, synaptic potential, axon hillock, do it again and again. And I mean, this can happen so fast that some neurons fire 50 times a second.